So this is in 11.4. We're going to talk about two tests today. They're called comparison tests. So the way the comparison tests work is I have my series that I want to know converges or diverges. And what you're going to do is you're going to compare it to another series, okay? So you're going to have two that you need to compare. So I'm going to start with the direct comparison test, which is sometimes just called comparison test. So it says, okay, if you have two series, suppose that I'm going to call the first one AN and the second one B sub n. These need to be series with positive terms. So if you have like an alternating series, you can't use this test for those. Your terms have to be positive. So there are two things that this test is going to tell us. It says if the series B sub n is convergent and comparison test means you need to compare the two, so I need to know that A sub n is less than or equal to B sub n for all n, then A sub n as a series is also convergent. Okay, so you have to have positive terms. That's an important thing to remember. Okay. So you have two series, you compare their terms through an inequality. AN is smaller than BN, less than or equal to. The bigger one converges, so the smaller one also has to converge as well. Okay. So the second thing I'm going to state, second part of this says if B sub n is divergent and B sub n is less than or equal to A sub n for all. Maybe I'll leave that the other way. I'll leave it as A sub n is greater than or equal to B sub n for all n, then the series A sub n is also divergent. Okay. So the second part says my other series B sub n is divergent, but A sub n, the terms are bigger than Bn. The Bn terms. So the smaller thing diverges, so the bigger thing has to diverge as well. Okay? All right, so let's take this direct comparison test and apply it to some problems. Okay? So the first one we're going to do, determine whether the series the sum from n equals 1 to infinity of 5 over 2n squared plus 4n plus 3 converges or diverges. So remember that this series is not a P series. If I just had n squared in the bottom, then it would be. Or even the 2n squared would be fine. But because I have this addition going on here, plus 4n plus 3 in the denominator, this is not a P series. Okay? So whenever you use a comparison test, you have to take your series and you have to come up with another one to compare it to, okay? You have to kind of like cook up another series. And usually it's for making small changes. So if I take away, I just said if this 4n and this plus 3 weren't there, it would be a P series, right? So that's what we're gonna do, is I'm gonna take away those two terms in the denominator to cook up a new, so my two series that I'm gonna have are this first one and then this second one. Okay? Now I need to figure out which one of these has, they're both positive, right? Do we agree that these series have positive terms? Remember, if they don't have positive terms, you can't use the comparison test, but they do. Great. So now I need to know which one of these is has larger terms. 2n squared. Compare this to 5 over 2n squared. So which one of these two do you think is bigger?
Second 2 is 5 over 2n squared.
Yeah, the second one, right? Because the one on the left has a larger denominator. The denominator is bigger, which means overall it's a smaller number. So exactly. The second one is bigger. It's actually just strictly greater than. I don't have to write equal to there. Okay. So now that I know the relationship between these two, I'm going to take my new series that I have, which is this 5 over 2n squared, and I've got to decide if that converges or diverges. So 5 over 2n squared. Well, you can pull out the 5 and you can pull out the 2. 1 over n squared. What do we have here? A P series. What's my value for P? 2. So does it converge or diverge? If it converges. If P is bigger than 1, it converges. So P bigger than 1, so it converges.
Does it converge to 2?
We don't know what value it converges to. Yep. So remember in my comparison test, I said if the bigger thing converged, the 5 over 2n squared, that's my bigger thing, it converges. So the smaller series has to converge as well. Okay. So the sum, 5 over 2n squared plus 4n plus 3 converges by the direct comparison test, which I probably will start abbreviating as DCT. Okay.
All we did was just split them up.
So what we did is we took our series and we created a new one from it by making a slight modification. I just removed some of the terms in the denominator. You want to make it so that, because what happens is if you look at the statement of our direct comparison test, I had to know that the one I'm comparing it to, I have to know if that one converges or diverges. That's that beginning statement in all of these. If Bn converges, if Bn diverges. So whatever I'm going to compare it to, I got to know if that converges or diverges. So by removing the two terms in the denominator, I'm left with a P series. which I know converges or diverges. Okay.
So do you always take the first term on the bottom?
So this is a special example of a rational series where I have a polynomial of n divided by a polynomial of n. And so what you can do is take your largest degree in the numerator and largest degree in the denominator sometimes. Kind of like your leading term. Okay.